Welcome everyone. So in this video, I want to take a look at another area where systems of linear equations have really nice applications, and that would be the study of networks and network flow. So a network is a system that consists of points that are called nodes with lines called branches that are connecting some or all of the nodes. So the social network, for example, would be an example of a network where each node would be a person, and maybe these people are connected by a line if, say, they are Facebook friends. So in this case, we don't see any direction on these arrows because I am not up to date with my social media. But as far as I know, on Facebook, you can only be friends with someone if they are also friends with you. You can think about another social platform like Twitter, where my understanding is you can follow somebody even if they are not following you, where then these arrows might have directions depending on, is this person following that person? If so, then we can put an arrow going that way. So a network is just a bunch of points and lines connecting those points. In situations where there is a direction, then we might put arrows on these lines to indicate the direction of the flow. And in many cases where we're using networks, we also have a flow. So for example, if we're studying traffic patterns in a city, then each node might be an intersection, and this might tell us, okay, we have 30 cars that enter this intersection each hour, and then we might indicate how many cars leave this intersection as well. So these flow rates might be given by a number, or if we don't know what that value is, then we might use variables as placeholders for those amounts. And the assumption here is going to be that the total flow into a network is going to equal the total flow out of the network. So for example, over here, we would see that with 30 is going in, then that should equal the sum of the stuff flowing out of this node. So that would be x1 plus x2. And the goal is going to be, if I know what the flow is in some branches of this network, then how can I figure out what the flow is in other branches of the network? And so various fields where networks have important applications might be electrical circuits, the flow of goods through supply chains, social networks, and the example that we'll take a look at next would be with traffic patterns, which could play an important role in urban planning. Okay, so let's take a look at an example of a network flow problem, in particular looking at the traffic flow. So on the left over here, we have a figure of some streets in downtown Baltimore. So each of these streets happens to be a one-way street. So Lombard Street goes this way, Pratt Street goes that way, Calvert Street goes this way, South Street heads down. And over here we have Inner Harbor in Baltimore. And maybe we know the flow rates into and out of some of these intersections, and others are not known. And so what we want to do in order to solve this problem would be, well, if I know what the flow rate is on this block, how does that help me figure out what the flow is going to be in some of the other unknown blocks? And what happens in networks is that the flow in and out of each node should be equal to each other. So let's take a look at, say, intersection A, which is right here, the intersection of Pratt and Calvert Street. And what I can see at this intersection is there's a flow rate of 300 cars or vehicles per hour that's going into intersection A. So that's the 300 over here. And from Calvert Street, we have 500 vehicles per hour going into this intersection. So altogether, we have 300 plus 500 going into intersection A. And the outflow is given by x2 and x1. So altogether, if we have 500 vehicles going into this intersection per hour, then x1 plus x2 should equal 500 cars that are flowing out of that intersection each hour. And so that gives us one linear equation for intersection A, which is dependent upon these two variables, x1 and x2. So namely, we see x1 plus x2 has to equal 800. And then we can move to intersection B, and do a similar balancing of inflows and outflows. So here's intersection B, Calvert and Lombard Street. And so at this intersection, we have an inflow of X4, we have an inflow of X2, and we have an outflow of 300 and an outflow of X3. So the inflow, X2 plus X4, that needs to equal the outflow, which is 300 plus X3. And so that gives us a second equation down below, namely X2 minus X3 plus X4 equals 300. And you can go through the other intersections, C and D. You might want to try and practice this yourself to come up with the balancing of inflow and outflow equations that we can then organize into a system of the 4 equations that we have down below in 5 variables, x1 up to x5. So each of these is for intersection A, B, C, and D. And then we also need to consider a 5th condition, which is the entirety of the system. So I have 300 cars per hour going in here, 500 going in per hour here, and 400 going in per hour here, and 100 going in per hour over there. So altogether, the sum of the flow into this system would be 300 plus 500 plus 100 plus 400, which gives a total of 1,300 vehicles per hour. And this should balance out with the flow out, which we have 300 going out per hour, 600 going out per hour here, and then we have X3 going out per hour there. So the sum of these flow outs should equal the sum of the flow in. And as a result of balancing the flow in and flow out for the entire system, we can see we get a fifth equation, namely X3 needs to equal 400 in order for the entire network flow in and flow out to balance out. So now we've got a system of 5 different linear equations with 5 variables that we'll solve on the next slide. Okay, and so we set up the following system of 5 equations and 5 unknowns, namely the top equation x1 plus x2 equals 800. Equation 2 is x2 minus x3 plus x4 equals 300. Equation 3 is x4 plus x5 equals 500. Equation 4 is x1 plus x5 is equal to 600. And then the 5th equation is x3 is equal to 400. And so from this system of 5 linear equations, we have an augmented matrix, which I've set up below. So the top row, 1, 1, 0, 0, 0, 800, comes from 1x1, 1x2, 0x3, 0x4, 0x5 equals 800. And the other 4 rows of the augmented matrix come from the other 4 linear equations. And so we can do elementary row operations on this matrix and do row reduction. And that results in the following reduced row echelon matrix that we see. And I've lost 1 row on this matrix. And that's because the very last row, once it's put in reduced row echelon form, is a row of all zeros. But if you want to be consistent here with our matrix size, then maybe we can leave that down here. But here we have our reduced row echelon form of this matrix, from which we get the following solution. So we can see, for example, that we have x5 is free because this column does not have any pivot in it. The other columns all have a pivot. So the variables x1, x2, x3, and x4 are all basic variables, but x5 is free. So what does this mean in practical terms? For example, if I know what the value of x5 is, then we can figure out the values of all of the other x's. Well, we know that x3 is equal to 400, but if I measure the flow of the traffic just on this one street, then I know enough information to figure out what the flow is on all of the streets. And thus we get a solution to this network flow problem relating to traffic in downtown Baltimore.